Hi, class. This is Mr. Hart. In this podcast, I want to go over some of the things we covered in week 2 on forces. And if you remember, last time we left off with the measuring weight lab, and I just wanted to continue from there and go over what we covered. So, if you remember, we did this little simulation that kind of reinforces the idea of um, what forces are acting on objects. The force of gravity, the normal force, applied force, and it kind of showed why certain things move the way they do, why they accelerate, why they don't. Okay. Also, kind of demonstrated friction. So if you were absent or like to review, you can go to FET's website and download that simulation. It's really good at helping us visualize these force diagrams we've been drawing. Okay. Then we did the notorious horse and cart problem. Okay. If you want to go to the simulation, it's at this address. Okay. It's on the CK12 simulation page. But a lot of students struggle with this problem because there's a lot of forces acting between the horse, the cart, and the earth. And so we had to draw 3 different force diagrams, one for each object: the horse, the cart, and the earth separately. Okay. And I really like this problem, even though it can be pretty hard for students, because it helps them realize the importance of Newton's third law. Because every force that acts has a reaction force. Okay, there's a force equal and opposite somewhere on another diagram. So for example, like the cart itself may have a force of gravity on the earth, or sorry, force of gravity from the earth. Okay, so it has a force pushing down. But that means the earth also has a force in the opposite direction going up, right? The horse may be trying to push forward on the cart, but that means it's also pushing on the earth this way. So it has an arrow going to the left, one going to the right, one going to the left. Um, the cart may be being pulled forward from the horse, but that also means that the cart is pulling back on the horse. So these 2 arrows are linked. These 2 arrows are linked. These 2 arrows are linked. Okay. Every arrow is going to have a connection. Every force has an equal and opposite pair. So most of the time we've just been drawing one free body diagram. Okay. But if you ever draw more than one in a situation, multiple free body diagrams, there's always pairs. Okay, forces always act in pairs because of Newton's third law. Okay, so if you haven't, if you weren't here to do that problem or would like to review, I recommend trying to do that problem with all the different force diagrams and seeing if you can find where all the paired forces are. Okay. All right, and then also if you're watching this video to make a participation, let's just do this review question. Okay, an object with a mass of 20 kilograms is pushed with a force of 480 newtons. What is the object's acceleration? Okay, then also try this one. A car pushes, sorry, typo. A car pushes on a road with a force of 500 newtons. We know that the road will push on the car with the same force because of A, Newton's first law, B, Newton's second law, C, Newton's third law, or D, Newton's law of gravitation. Okay, so think about that for a second. And if you answered C, Newton's third law, you are correct. Okay, because we know that forces act in pairs. All right, then we did this review question. If an object cannot exert the same amount of force as is applied to it, then it A, moves, B, brakes, C, accelerates, or D, stops. Okay, think about that for a second. Now, if you put A or C, then you're wrong. Okay, the object will not necessarily move or accelerate, but if it cannot exert that same amount of force that's applied to it, it actually breaks. Okay, so this one's kind of confusing to some people because they think, oh, if that object's not pushing back with the same amount, it's going to move forward. But no matter what, even if you're moving an object with the force, it's still going to push back with the same amount. Okay, it's kind of confusing that it can be pushing back with the same amount and still be moving. Okay, but that goes to the pairs on different free body diagrams. Okay, but if it can't apply that same force, if it can't do what Newton's third law says and push back with the same amount of force, then it's actually going to break. Think about punching through a wood block like they do in the karate movies and stuff. If you just punch the block softly, you're not going to break it. It's not necessarily going to move. because it's applying the same force back. But if you can punch hard enough, get enough force on it, then you can actually break the board, right? When the board can no longer apply the same force that you are applying to it, it breaks. Okay? So hopefully that makes sense. And think that through for a long time if it doesn't, because that's a really important concept. Okay? Then we talked about the different types of forces. Yeah, you probably are familiar with most of these, but let's just go through them. So there's the first one that we covered is the gravitational force. Everyone's pretty familiar with what gravity is. It's a force pulling down between you and the earth. Okay? You pull down the earth pulls down on you, you pull up on the earth, but the earth doesn't accelerate because it's so big. Okay? And then we had the normal force. That's the force an object exerts in the perpendicular direction to the surface. Okay, so if I put a book on the table is going to push up on the book. Okay, it doesn't like being pushed on, so it pushes back. Okay. Then we had friction. Okay, so friction is the force caused by resistance to movement across the surface. It often causes heat. Okay, so if you look at the surfaces on our scale, on a macro scale, we might think surfaces are pretty flat, but if you really look on a microscopic scale, they're pretty rough. Okay, so that the collisions between the different parts of the surface is what causes that friction, which causes that force, okay, that doesn't want it to move. Okay, so friction is a big force that we cover and we see in daily life. And some people think life would be better if we didn't have friction, but think about what the world would be like if we didn't. Okay, we couldn't stand up, we'd slide to the ground, we couldn't hold on to things very well. You couldn't push on something without it going flying and you going flying too. Okay, it'd just be really nasty. Not so. Friction's kind of a love-hate relationship for physicists because we know we need it, but at the same time, it's kind of hard to deal with some applications. Okay. Then there are other forces where like an applied force. Okay, simple enough, hitting something with a hammer, punching something, pushing something. Okay. There's also tension. Okay, that's a force from something being stretched that wants to go back to its normal shape. So like a rope has a force. Okay, bungee cords have tension. Okay, they want to go back to their normal shape. Similar to that is like a spring or elastic force from compression. Okay, something you compress something, it wants to go back to its normal shape. Okay, and then the last one we cover is electric and magnetic forces. So if you think of two magnets, they can have a force on each other. Okay, can bring things in together. Okay, and last of all, I talked about some of the assumptions we make about forces, like objects not being shaped. You know, we usually make the assumption that they're at the center. Okay, or they're very small, or they're a dot. You know, we're making a lot of assumptions when we talk about forces, but still we can figure out a lot of interesting facts by doing these free body diagrams and doing the calculations. Okay? And that's all we covered for forces in this week. So hopefully that made sense, and thank you for watching.